Thank you. Welcome, everybody. My name is Heide Ibrahim. I'm the scientific coordinator of ALLS and also the project manager to upgrade the facility to ytterbium high average power lasers. It's my pleasure to talk today about Coulomb explosion imaging experiments I have been leading in ALLS in the recent years. We will go from molecular movies to a molecular road movie. For now, I invite you to follow your imagination what a molecular road movie might be. In general, a road movie is about somebody who leaves conventional paths and explores new perspectives. And surprisingly, this can also happen within molecules. Filming a molecular movie compared to molecular road movie is like imaging planets, where we know where and when to find them, compared to imaging shooting stars, which can be almost anytime, anywhere. Here you will see one example of a conventional, so mainstream molecular movie. We have heard even Hollywood is interested in molecular movies now, which shows proton migration in the acetylene cation. And we have been filming this a few years ago in experimental collaboration with a group of Joe Sanderson from University of Waterloo. At that time, it was believed that proton migration in the acetylene cation can only be triggered using free electron laser pulses, since one needs to reach the first excited state here. But we have shown that also using 266 nanometer pulses, we could, in a multiphoton excitation, reach this state as well, initiate a wave packet which undergoes through a conical intersection towards the vanillidine isomer and also back towards the acetylene configuration. We probed this using ultra-short 800 nanometer pulses to blow up the molecule. We are collecting positively charged fragments in Coulomb explosion imaging. And now we can correlate these fragments. And whenever we find pairs or triplets whose sum is 0, we know that they must have originated from the same molecule. So for example, when we correlate CH plus and CH plus, then this is an indication for the acetylene configuration, while C plus CH2 plus would be an indication that the proton has reached the other side and we are in the vanillidine configuration. By doing so, we could identify acetylene and vanillidine contribution changing. At about 100 femtoseconds, the vanillidine maximum is reached, and Michael Skurman did a great job in supporting the theory here. So this was tricky in one sense, but it was also easy in another sense, since we knew what to look for and where to find it, because it's a coherent motion we have been looking at. This is different in the case of weak statistical dynamics I'm going to talk about in the second example that are hidden behind overwhelming backgrounds. And by statistical, I mean the opposite of a coherent wave packet dynamics. So we have an ensemble of molecules and each member of this ensemble can start its own motion at its own time. But as was also identified in this paper by Andre Staudte and Albert Stolow and co-workers, Coulomb explosion imaging is a fantastic means to study such statistical dynamics, because the method is sensitive to single molecules and we can select specific channels and like this get rid of a background. So the example we have been looking at is the unimolecular dissociation of formaldehyde, which consists of conventional dissociation following minimum energy paths. And this is shown here for the radical channel in which a bond is stretched until one proton can leave, or for the molecular channel, which has to overcome a barrier, and then we have H2 and CO molecular fragments. But it was shown in 2004 that in addition to this, there's also a third path, the roaming channel. And in this channel, one fragment is exploring the potential energy landscape and is encircling the remaining HCO fragment in its own way. So one example trajectory is shown here on the right, but there are many different possible ways how this could occur. In general, roaming involves large amplitude motion far from the equilibrium geometry, bypassing the traditional constrained transition state. It's of almost general nature, so it can occur in a variety of molecules, not only formaldehyde, but also acetaldehyde, methanol, or NO3, for example. And it's also not only the light proton that does this roaming motion, it could also be H2 or O, for example. It's observed so far in high resolution spectroscopy in an indirect manner, so looking at spectroscopic footprints, and then, for example, a specific combination of CO and H2 rotational and vibrational levels would indicate roaming. It's also been in other molecules, there have been attempts to study it in a time-resolved way, but also these succeeded only in an indirect manner. So there was no direct observation of the roaming fragment, the roamer itself. Imaging roaming dynamics is challenging. In the case of formaldehyde, we need to find a way to image statistical dynamics. We have already talked about this using Coulomb explosion imaging. This is a way how it can work. But then there's also ultrafast dynamics extending from femtoseconds to nanosecond timescale, which is kind of challenging combination. So with the help of Michael Scorman, again, we could identify the paths involved. So we start from the ground state using 304 nanometer pulses. We pump to the A state, to the excited state here. But the actual roaming and dissociation dynamics would occur on the hot vibrational ground state. So the wave packet first has to relax back there. And previously it was assumed that this has to take tens of nanoseconds. However, with Michael's help, we could figure out that it can already occur in hundreds of femtoseconds if specific vibrational states are coupled to each other. And this is indeed the case since we are using femtosecond pulses. So once we are on the hot vibrational ground state, now the dissociation can occur. In the case of roaming, for example, there would be first H2 vibration triggered, and then one of the protons takes off and starts a journey until it might grab off a second proton, and both of them are leaving the CO fragment together. And we use a time-delayed probe pulse to probe this procedure. But of course, we cannot follow a single molecule along its whole path. We can only take snapshots of many molecules on many different roads. So basically it's a mess in the end, right? So, and what makes it really annoying is the order is fixed. So there would not be H2 formation before roaming, but the onset and the duration of steps 1 to 4 is statistical. So in order to find a good experimental observable, we had help from theory, first from Paul Houston, who provided semi-classical trajectory simulations, and Tomoyuki Endo, the postdoc I was working with, was then able to find a way by sorting them in real space to identify different occurrence areas, like highest probabilities basically for the different channels. So in such kind of plot, the CO would be located at the 0,0 coordinate. The one proton, the closer one to the CO, is along the positive x-axis, and then the other proton would show up, in the case of roaming, for example, at a distance of a few angstrom around the CO fragment. In the case of molecular dissociation here, both protons are leaving together, or actually deuterons in the experimental case. In the case of radical dissociation, it would explore a larger space. And then for equilibrium, all fragments are very close together. And then we have been using this information to simulate the actual probe step. So to simulate the Coulomb explosion on a realistic D2CO3 plus potential with the help of Joel Bauman's group from Emory University. And we could identify that the kinetic energy release versus the momentum vector between the two deuteron momenta is a very good observable, because all these different paths we have identified in real space show up in different areas here. So for example, in the case of equilibrium, fragments are closest together. So in this case, we would observe the highest kinetic energy release. For radical dissociation, the fragments are far away, so kinetic energy release is low. And then we also see the spots for roaming and molecular dissociation. So let's have a look at the experimental data here. We see 6 different plots for different time delays after background subtraction. At the highest kinetic energy is the equilibrium. The lowest corresponds to the radical dissociation, as we had identified. And then in red, we have roaming, and in blue, the molecular dissociation channel. And yeah, they show up at the same kinetic energy, but luckily we were able to separate them in the angle between the two deuteron momenta. And we could prove this in the paper here below. Surprisingly, there is really a huge amount of roaming showing up. So this blob I'm indicating here right now, this blob, they correspond to about 70% of the counts within this range. And That is much more than we expected just from the trajectory calculations on the hot vibrational ground state. But the reason for this is that the roaming distance is exactly what ionization likes. So it's the distance of a few angstrom, and this is where we observe enhanced ionization. So our experiment actually favors roaming over the other dissociation pathways. And that's a very nice side effect. So to summarize, basically the paper, also aspects I had no time to talk about, we have been able to directly observe the roamer and also dissociating fragments. And we could generalize the roaming definition because previously it was assumed that roaming would always lead to molecular dissociation only, and we could show that it might also lead to radical dissociation. And we were able to observe completed but also uncompleted roaming paths because not all of these fragments continue on the roaming path. Some might return and say, oh, it was nice where I've been before. But because we're able to observe transient features, we could also find these. The onset of roaming occurs several orders of magnitudes earlier than expected because the onset of the A to X transition is already on the hundreds of femtosecond rather than nanosecond timescale. And this provides a perspective for detecting roaming dynamics in particular, but also weak statistical dynamics hidden behind overwhelming stochastic backgrounds in general. And of course, in order to get a good molecular movie, you need a fantastic film crew. Tomoyuki Endo, the postdoc who was leading the effort in the lab and also did a fantastic job in analysis and modeling. He had great support by many people, and I like to highlight Paul Houston, Joel Baumann, and Michael Skorman's groups for the theory support, and François Légaré was supporting this whole project in a fantastic way from the ALLS side. But of course, the real star of this is the formaldehyde molecule. And if you like, I invite you to check out this video on YouTube, which shows a short animated molecular road movie showing this little guy here. Of course, we had different production places and financial support, and I'm very happy about this. And just quickly looking into the future. So far, I've been using Coulomb explosion imaging, so I was restricted to ions. In the future, as Joe mentioned, we will have the Coulomb et al.'s, and then we can identify ions and electrons in coincidence. And so far, the repetition rate of 2.5 kilohertz was not bad, but of course, 20 to 100 kilohertz, which would be much better in order to get better statistics. And I'm dreaming of going towards bigger and bigger molecules, that one day even biologically relevant molecules, and then to study them, like to study, for example, radiation damaging effects or also coherence features on them. But of course, coming back to the picture of the planet and the shooting star, well, this is a long way. Thank you very much.